Can you guys hear me?
Yes.
All right. I am going to go to chapter 5 slides and continue what we are doing in the last class period. Do you have any questions?
No, sir.
All right. I'm going to share my slides right now. We left last class period. We talked about kinetic molecular theory of gases, liquids, and solids. We're going to talk about intermolecular forces today. Can you see my slide on intermolecular forces on the screen?
Yes.
All right. There are 3 types of intermolecular forces. They are electrostatic. That means they are attraction between positive and negative charges present in molecules. The 3 types are hydrogen bonding. First one is hydrogen bonding. Second one is dipole-dipole interaction. London dispersion force, third one. The first two are dipole, basically DD. DD means dipole-dipole. The hydrogen bonding is mainly stronger dipoles. Hydrogen bonding is NH, OH, FH dipoles. The electronegativity difference of fluorine, oxygen, and nitrogen are the largest. Therefore, these dipoles have strong polarization. Therefore, when they participate in attractions, like here in water molecule, they are called hydrogen bonding. The second one, dipole-dipole attraction, is all the rest of dipoles which are weaker than NH, OH, and FH dipoles. The hydrogen bonding is little stronger than dipole-dipole interaction because of the weak nature of the attraction between these dipoles in the acetone molecules. This is the acetone molecule. There's a dipole between carbon and oxygen. It's attracted to dipole in the next molecule through the oxygen of the first molecule to the carbon of the second molecule. So that's how you get dipole-dipole attraction. Strong attractions between dipole are called hydrogen bonding. Hydrogen bonding is NH, OH, and FH attraction. The third one, which is weaker, is called London dispersion force. We call it LD. Hydrogen bonding is called HB. So we're going to look into these 3 intermolecular forces that are present in liquids and solids. In gas phase, these intermolecular forces are weak because gases are constantly moving. Kinetic energy is high. Therefore, they disrupt the intermolecular forces. So let's compare these weak intermolecular forces, these three intermolecular forces, to bonding forces called interatomic. In ionic compounds, ions get attracted, cations and anions. They are very strong compared to intermolecular forces in here, which are weak. Ionic bond is the strongest. Ionic bond is not the intermolecular force. There's an interatomic. They are bonding. When you look at the covalent bonding, it can form single bond, double bond, triple bond, etc. So they are little weaker than ionic bonding. So relative to covalent ionic bonding, intermolecular forces are weaker. There are three types: hydrogen bonding, dipole-dipole interactions, and London dispersion. Let's start with the weakest one, which is called London dispersion force. They are present in all molecules, but when the molecule has polarity, its effect is not shown. So let's look at London dispersion force. London dispersion force is the weakest one. That's present, only shown up in non-polar molecules. This is a non-polar atom. Normally, electronic distribution is uniform, but temporarily, polarization can take place. That means polarization means instantaneous movement of electrons in the electrons shifted to one side, move away from this side, create positive end of the charge distribution and a negative end of the instantaneous temporary positive and negative charges. In another molecule, which is adjacent to the first one, these negative charge and positive charge can interact and create a force that electrostatic in nature. That's called the London dispersion force. This is a temporary force. It depends on the instantaneous fluctuation of polarizations in a non-polar molecule. It's the weakest. It's shadowed when other forces are present. We don't talk about London dispersion forces if molecule particles have intermolecular forces, dipole or hydrogen bonding. Therefore, they are ignored, but they are present in all molecules. When non-polar molecule where there's no dipole or hydrogen bonding, effect of London dispersion forces can be seen. As I said in the previous slide, found only among the non-polar molecules. They are present, but they are not showing up because they are weak in polar molecules. London dispersion forces exist between all atoms and molecules, regardless of non-polar or polar. But polar molecules, they are not significant. Therefore, we ignore them. There are only forces of attraction between non-polar molecules. Non-polar molecules only have dipole London dispersion forces. They are weak. It's between 0.1 to 2 kilocalories. Hydrogen bonding is 10 kilocalories. So therefore, it is weakest. Dipole is in between, about 1 to 6 kilocalories. Their strength increases as the mass and number of electrons in a molecule increase. This temporary fluctuation of charges are affected by number of electrons. Heavier the formula mass, more electrons are present in the molecule. Therefore, London dispersion forces increase when the atomic mass of the particle of the gas phase increase. These forces are very weak. They contribute significantly as active forces. When molecules become large and attraction can take over a large surface area. We're going to talk about how the attractive force become larger due to more electrons and distribution of these charges over a large area, how that affects London dispersion force. The second weakest is dipole-dipole interaction. It's found only among polar molecules. As the name says, this is permanent dipole-dipole, unlike London dispersion that are temporary fluctuations in. Therefore, they are weak. Dipole-dipole attractions are permanent nature, electrostatic attraction between permanent dipoles. If you consider butane and acetone, they have similar molecular weight. Why we always worry about molecular weight? Molecular weight affects number of electrons. Molecular weight is half the atomic number. Therefore, have the molecular weight also approximately number of electrons. As the molecular weight increase, number of electrons increase. Therefore, it can affect intermolecular forces. If you look at the butane molecule, there are 4 carbon atoms. They are non-polar. This is polar. Acetone is polar. Because this CO bond contribute to the overall polarity of the acetone molecule. We talked about this in chapter 4. Therefore, the intermolecular force present is London dispersion force, non-polar molecule. Therefore, boiling point is smaller than boiling point of acetone, which is 58. Boiling point smaller means weaker London dispersion force. Higher boiling points are coming from dipole attraction in the acetone molecule. If you have water which has a hydrogen bonding due to the OH dipole, water is 100 degrees Celsius due to hydrogen bonding. So you can look at the formula and do a structural formula and figure out whether the molecule is polar or non-polar, whether it has hydrogen bonding or dipole or London dispersion force, depending on the structure. Butane is a non-polar molecule. The only interaction between butane molecules are London. Therefore, weaker intermolecular force. Therefore, it has the lowest boiling point. Acetone is a polar molecule. In molecules are held together in the liquid state by dipole-dipole attraction. Therefore, it has higher boiling point. The strongest intermolecular force is called hydrogen bonding. We already talked about hydrogen bonded to highly electronegative atoms. That's fluorine, nitrogen, and oxygen. These three, when bonded to hydrogen, they form strong dipoles. They are called hydrogen bonding. I wrote down here again. Partial negative charge on oxygen, nitrogen, or fluorine atoms. You write down delta negative, delta positive, so on and here. These are stronger interactions between stronger dipole, therefore they affect the physical properties of the liquid to a great extent than other two. In this diagram, first diagram, which is the kind of formula, second diagram is ball and stick model of water. It shows the hydrogen bond between oxygen negative charge and the positive charge on the delta positive charge on the hydrogen, forming the hydrogen bond. There could be approximately 3 hydrogen bonds, like shown here. So that's how water molecule is attracted to other water molecules in the liquid water. Hydrogen bond energy is stronger than other two. It's between 1 to 10. Water is 5 kilocalories. Some stronger ones, hydrogen bonding, could create 10 kilocalories. Compared to hydrogen bonding, covalent bonds are much stronger. However, covalent bonds are interatomic. They are not intermolecular forces. Hydrogen bonding, even though it's less than covalent bonds, in liquid water, it has great effect, important effect on the physical properties of water. Water has highest specific heat. Therefore, water can absorb heat from the atmosphere during the summer over the oceans and store heat during the summer. When the winters get cooler, oceans can release the heat and maintain the thermal equilibrium on the, that means sudden temperature fluctuation would not take place. Therefore, it's very important. Also, hydrogen bonding between water molecules form when ice is formed. Hydrogen bonding create more volume in the liquid water or ice, more volume than the water. Therefore, density of water is greater than density of ice. Ice floats on water. This has important consequences. When a lake freezes, it freezes from the top. Top ice is formed because ice has lower density than water. Therefore, when a lake freezes, there could be water below the ice layer. Therefore, aquatic life can survive during the winters. This is very important. Hydrogen bonds are not restricted to water. There are NH groups in DNA molecules. DNA is found in the nuclei. They are the hereditary material that pass information from one generation to the other. They are made up of double helix structure. There's a two strand of DNA are attracted to NH hydrogen bonding of the base pair, hydrogen bonding in the base pair between the two strands. These base pairs are called ATCG, adenine, guanine, cytosine, thymine. So that is very important attraction to maintain the genetic DNA structure of the genetic material. Let's answer a few questions. In the liquid state, disruptive forces are called kinetic energy. Attractive forces are called intermolecular forces. In a liquid, destructive forces and attractive forces are about the same. So they're asking about the liquid state. They are same. In a gas phase, destructive forces are dominant over cohesive forces. Therefore, gases don't have intermolecular forces. So for this question, liquid state, this statement, first statement, roughly the same magnitudes as cohesive for the correct answer. They are not weak compared to cohesive forces. In solid, this is true. Solid have cohesive forces, overcome the disruptive forces and liquids become solid. This is a gas. Gases have dominant cohesive forces. This is solid, dominant over cohesive forces. This is gas, correct. Disruptive forces are dominant over cohesive forces. Therefore, answer is A. In a molecular system, kinetic energy is associated with, is considered to be disruptive. It disrupts the intermolecular forces. This is a true statement. They're asking whether it's true or false. The potential energy of great importance, potential energies, the attractive forces, when considering the state associated with electrostatic interaction. These are the three intermolecular forces. It's a potential energy. That's the true statement. Potential energy of great importance when considered. That's a true state. Macroscopic properties of the liquid state include liquid state don't have definite shape. Definite volume is correct. Therefore, wrong and right make it wrong. Therefore, wrong or false statement. Kinetic molecular theory and how it affects physical state of a matter. Which of the following description only apply to gaseous state? If you look at this, gaseous state, that's not true. Gaseous state don't have definite shape. Indefinite volume, that's true. Disruptive and cohesive forces, this is not true. Gaseous state, disruptive forces are greater than cohesive forces. Pressure change significantly as the volume increase. That's true. Therefore, there are two, this is not true. Definite shape, indefinite shape, definite volume, that's not true. Therefore, answer is C. Gases change significantly. Pressure change significantly affect the volume of the gas. Which of the following description apply to matter in the solid state? Solids have definite shape and higher density. That's true. Cohesive forces are dominant over disruptive forces. That's true. Kinetic energy dominate over potential or cohesive forces. No. But there are two correct answers, A and B. Therefore, answer is more than correct answer, D. We're going to look into characteristics of different states of matter. We go a few more questions. For the state with definite shape. Select the states from the following list. State with indefinite shape. Select. Indefinite shape is gases and solid. So both gases and solid. Solid has definite shape. Liquid have indefinite shape. Not only that, both liquids have, gases also have, both liquid and solid state. That's not true. Therefore, answer should be D. For the state with definite volume, select the state from the list. Definite volume. Which one has definite volume? Liquid and solid have definite volume. Liquid only, no. Solid only. But both liquid and solid have definite volume. Answer is C. For the state where cohesive forces, there's attractive intermolecular forces, dominate kinetic energy, disruptive forces. Where the cohesive forces, that's a solid. Only solid has cohesive forces that dominate over disruptive forces. That's the solid only. Both. So answer should be B. For the state where potential energy dominates over kinetic energy, when the potential energy, that's a cohesive forces, kinetic energy, that's the solid state only, also solid state. That's also correct choice. It's D. For the state where particles are relatively close together, select the state from the list. Particles are relatively close together. Both liquid and solid have particles relatively close together. Therefore, answer should be C. Both liquid and solid state. The phrase, question 159. The phrase, particles close together, held in fixed position, and fills the container applied to, there are two statements. Fixed position is solid, fills the container, applied to solid. Particles are fixed position and completely fill the gases, completely fill the. Therefore, B should be the answer. We're going to go a little more, some more problems about intermolecular forces. Intermolecular forces differ from intramolecular forces. That's a covalent and ionic bonding. Interatomic. Intra means between atoms. Between molecules is three forces. Hydrogen bonding, dipole, London dispersion. Intermolecular forces differ from intramolecular. They occur in only liquids. Intermolecular forces occur in liquids. Only doesn't seem to be good because solid also have intermolecular forces. They are much stronger. That's wrong. Intramolecular are not strong than intermolecular. Therefore, this one is questionable. Solid also. They only occur when the hydrogen atom present. Intermolecular forces can happen without hydrogen atoms. Hydrogen not necessarily guarantees intermolecular forces. More than one correct response. There's no correct response. All these three, A, B, C, are not correct. Therefore, correct answer is no correct response. In which of the following pairs of molecules would the first listed member of the pair have higher boiling point than the second listed pair? So this has HF dipoles. That's hydrogen bonding. HBr is a dipole-dipole. Therefore, this is correct. First molecule have higher hydrogen bonding, therefore higher boiling point. This is London dispersion. This has also London dispersion. But this force is greater because there are many electrons, more electrons in chlorine, non-polar diatomic chlorine, than non-polar diatomic fluorine molecule. Oxygen is London dispersion. NO is a polar molecule, therefore dipole-dipole. There's no hydrogen bonding. Therefore, this one is wrong as well. Therefore, only correct answer is A. Which of the following is strongest intermolecular attraction? Strongest is hydrogen bonding. Dipole is there. Covalent bonding is not an intermolecular force. We are asking intermolecular interaction. London dispersion is the weakest. D is the correct answer. Which of the following is usually the weakest intermolecular interaction? That's London dispersion. Covalent bonding is not an intermolecular force. Therefore, C is the correct answer. Which of the following influence the strength of London dispersion forces? Number of electrons? Yes. Size of the molecule? Yes. Shape of the molecule? Shape, flatter molecules have more surface area. So they can attract to the instantaneous dipoles. Therefore, all these three affect the strength of the London dispersion force. Answer is D4, 184. We're going to look at molecular structure and figure out what intermolecular forces are there and talk about boiling point, melting point, physical properties. First, 166. Which compound has the lowest boiling point? The lowest boiling point has the lowest intermolecular force. You look at these four molecules. That's the hydrocarbon. Hydrocarbon is not polar, therefore it's London dispersion. OH bonds there, the second one. That's hydrogen bond. That's carbon oxygen dipole. That's dipole-dipole. Third one, fourth one also has a dipole-dipole. Therefore, this is London dispersion, this is hydrogen bonding, these two are dipole-dipole. The lowest boiling point is London dispersion. London dispersion is the lowest intermolecular. So, answer to the question is lowest boiling point is A. Highest boiling point, same question. Now you have to look for one with the strongest dipole. Strongest dipole is hydrogen bonding, OH. Therefore, these two are not the highest boiling point. Highest boiling point is B. When octane evaporates, what kind of attractive forces are overcome? Octane is a carbon compound. Carbonate and hydrogen. Therefore, carbon-hydrogen compound, hydrocarbons are non-polar. Non-polar has only London dispersion. Covalent bonding between carbon-hydrogen atoms. Covalent bond nothing to do with attractive forces in a molecule. That's not the. When octane evaporates, it don't break carbon-hydrogen bond. Hydrogen bonding between octane molecules. There's no OH dipole. That's not the answer. Dipole. There's no dipoles in the octane molecule. Octane is similar, have more carbon atoms. Like butane, they have 8 carbon atoms. C is dipole-dipole interaction. Therefore, it's not the correct answer. Between octane molecules, there are London dispersion forces, non-polar molecules. Therefore, it's the correct answer. D is the correct answer. Which molecules exhibit London dispersion force? If you look at all these, they exhibit, they're not asking whether it affects boiling point. I was trying to get this point. I was trying to say all molecules, regardless of non-polar, polar, have London dispersion. But London dispersion is important when there's no hydrogen bonding or dipole. It's present in all molecules. So all molecules exhibit is the correct answer. Any molecule can exhibit London dispersion, but their effect is not shown when there's hydrogen bonding or dipole-dipole. Answer is C. Which molecule exhibit hydrogen bonding? If you look at these molecules, this is not hydrogen oxygen. Hydrogen bonding need to have OH dipole, NH dipole, or SH. This don't have OH dipole or any of those other two. Has NH dipole. Therefore, hydrogen bonding is shown by ammonia molecule. Answer is C. We're going to look into liquid state. We talked about 3 types of intermolecular forces. Hydrogen bonding, dipole-dipole attractions, and London dispersion. When you look at liquid state, as the pressure is increased, the real gas get closer, and the mutual attractions between molecules become important. That's when the gas becomes liquid. Liquid state is produced from gaseous state when you cool down or increase the pressure. When the distance decreases so that almost all molecules touch each other, then gas become a liquid. We call it condensation. Gas condenses to a liquid. In a liquid, there are little space between the molecules. There's very little space. Therefore, liquid cannot be compressed. Therefore, they have definite volume, like solid liquid. They cannot be compressed. The density of a liquid is much higher than gas. Gas is, particles are occupying a lot of space, their volume is large, therefore lower density. Liquid density is higher. When gas becomes a liquid, density becomes higher or occupies much smaller space than the gaseous state. Position of molecules in a liquid is random. There are irregular shapes around the particles of liquid, so they can slide over each other and they become fluid. You can pour liquids into another container because of this fluidity, irregular shape. That also gives rise to flow properties of liquid. Some liquids are viscous. They roll over each other, but the intermolecular forces are stronger when liquid has resistance to flow. Viscous material, viscosity is liquid that flow, resistance to flow is higher. So that's how the liquid state is described by this description, how a gas become liquid and properties of liquid. One of the properties of liquid is surface tension. What is surface tension? At a molecular level, surface tension is shown by liquid surfaces. The insect walk on water. How many of you seen some insect have wax feet? They can walk over the surface of water. Because water has almost a skin on the surface of water. That's due to the surface tension. It is an observation that layer of the liquid produced by uneven molecular attraction in the surface. Now let me describe this. If you have a surface of water in a beaker, this surface atoms have forces attracting on the surface and attracting into the. Therefore, surface look like a skin. That is the surface tension. If you have a capillary tube, water and glass, how many of you seen that they become meniscus? Glass and water. The cohesive forces between these are much higher than between water plus water. Therefore, the meniscus become like this. This force is higher at the end. This force is weaker. Therefore, meniscus like this. But mercury, if you put mercury in a tube, its meniscus is upside down. The mercury glass, cohesive forces, this one is less. This is greater. This is less than. So, surface tension is used to explain a lot of properties. Capillary action, how a water passes through a trunk of a tree, is there are cells called phloem. Phloem. You heard about that? Cells have long cells that that passes the water up to the tree. This is capillary action. If you put the water, there's extra pressure that pulls up water in the capillary tube. So these are due to, let's look at this in a picture wise. Pull a molecule on the surface toward the interior of the liquid. These pull crowd the molecule on the surface and create an elastic skin-like layer. That's surface tension. Surface tension is directly proportional to the strength of the intermolecular attraction between molecules. Water molecules attracted to each other, intermolecular forces, and water molecules also get attracted to gas much higher than water. Therefore, meniscus is concave. Let's look at the picture. This picture shows on the surface, this is inside. The forces are balanced. On the surface, the outside there's no force. Therefore, it pulls out. Therefore, these two forces pulls the water molecules in the direction of surface, create a skin-like surface. So we talked about surface tension. I'm going to talk about rest of it. Now we're going to look at another property of liquid. It's called evaporation and condensation process. When a liquid becomes a gas, it's called evaporation. When gas becomes a liquid, it's called condensation. The important property of the liquid is evaporation. In a liquid, there is distribution of kinetic energy among all molecules in the liquid, just like in a gas phase. The molecules are moving. They hit each other. On the average, kinetic energy is same. But some molecules have higher, some have lower, then the average kinetic energy is the same at particular temperature. Some of the particles can have higher kinetic energy, and others have slow kinetic energy. On the surface of the liquid, particles moving slowly cannot escape the liquid. They stay in the liquid. However, rapidly highly moving with higher kinetic energy can, on the surface, can escape to the gas phase above the surface of water. That's called evaporation. Also, condensation is some in the gas phase could come back and go into the liquid phase. That's the condensation. When you cool a liquid solution, the more gas from the top of the surface goes into the solution liquid. Evaporation and condensation are related to vapor pressure of a liquid and the boiling point. Vapor pressure is important in defining boiling point of a liquid. If a container is open, if you have an open container, liquid's there. If you leave it open, then slowly liquid moves into the gas phase on top of the layer and escape until all molecules are gone. If you leave a beaker of water for a long time, it will evaporate. But if you have a closed container, put a petri dish or close the container, then molecules remain in space above the liquid. And that creates a vapor pressure, which is at equilibrium between condensation and evaporation. So there's a certain amount of vapor pressure at a particular temperature above the solution of a closed container. The partial pressure exerted only by the liquid is called the vapor pressure of the liquid. Why we talk about partial pressure? In the next slide, we are going to show that on top of a solution, there could be nitrogen and oxygen in the air. Therefore, pressure measured on the top of the solution is partial pressure. Now vapor pressure increases with the temperature because more the molecule kinetic energy, higher the temperature. Therefore, more molecules escape into the surface. Vapor pressure increases with temperature until it's equal to atmospheric pressure. If you keep heating a liquid in a water, liquid in a beaker, the vapor pressure will increase. And when it become equal to atmospheric pressure, it starts to boil. Boil means direct conversion of liquid to a gas take place. Boiling point of a liquid is defined as the temperature at which the vapor pressure of a liquid is equal to atmospheric pressure. Therefore, boiling point of a liquid depends on atmospheric pressure. How many of you heard about this? Water boils on higher elevation at lower temperature. Therefore, when you cook something in the top of a mountain at high elevation, you have to cook more times. The cake should be baked because the temperature will be lower where the boiling takes place. Now let's look at the evaporation condensation in an open container. This is the liquid. Liquid particles are these are oxygen and nitrogen here. This is the liquid particles on the surface of water. These pink balls. The vapor pressure of the pink balls are called partial pressure of the liquid. Some molecules at the surface of the liquid are moving fast into the gaseous phase. So as the temperature increases, more evaporation. When the partial pressure of the pink ball or liquid molecules of the vapor are equal to atmospheric pressure, then the liquid start to boil. That's a direct conversion of liquid to a gas. It's the boiling. That's how we look into partial pressure on the surface of a liquid solution. In this picture, there are 4 compounds: chloroform, ethanol, water, and acetic acid. When you look at them, acetic acid has higher boiling point because hydrogen bonding is the intermolecular force in acetic acid. So is the hydrogen bonding is the intermolecular force, hydrogen bonding in water as well as. Ethanol is hydrogen bonding also. Chloroform has dipole-dipole. Therefore, lowest, this is the 1 atmospheric pressure, this line. When the temperature is that line, the liquid get converted to vapor directly, boiling take place. So this is the pressure on the top of the container. As you increase the temperature, this is the equilibrium between the vapor pressure increase at the temperature. Equilibrium vapor pressure increase. And when the temperature reaches 760, molecules start to boil. That's the boiling point of these substances. This shows boiling point is defined as the temperature of vapor pressure, which is equal to 760, this line here. So you can compare intermolecular forces with the boiling point or vapor pressure of the liquid. In this diagram, same 4 compounds are shown. The chloroform is a dipole-dipole polar molecule. This is hydrogen bonding. Water is also hydrogen bonding. Acetic acid is hydrogen bonding. Acetic acid molecular weight is 60. When the molecular is lower, something has higher boiling point. That indicates higher intermolecular force. When the molecular weight is higher, lower boiling point, it shows weaker intermolecular force. So these are hydrogen bonding, lower molecular weight than 120 here. But still they are higher boiling point. So you can compare molecular weights and explain the normal boiling points in terms of hydrogen intermolecular forces. Effect of intermolecular forces on boiling point. If you look at methane, molecular weight is 16, boiling point is negative, water is 18, which is almost similar, 16 to 18, it's 100. That shows methane should have weaker intermolecular. Methane has no polarity. It's a non-polar molecule, therefore London dispersion. Water has polarity and shows hydrogen bonding. So you can compare different material with the molecular weight and boiling point and explain in terms of intermolecular forces. The boiling point could be explained. Methane has 164. Hexane has 69. This hexane has 6 carbon atoms. London dispersion, both London dispersion. When the number of electrons increase, when the formula mass increase, number of electrons increase, London dispersion force becomes stronger. Therefore, hexane have higher boiling point. If you look at methane, this is smaller. This is large amount of electrons. Therefore, this can have greater London dispersion force than the methane. Therefore, hexane have higher boiling point. I'm going to talk about molecular shape. When molecules are similar in every other way except the shape, London dispersion determines the boiling point. Let's look at an example. That's pentane. This is called 2,2-dimethyl propane. This also have same molecular formula. 5 carbon atoms. 5 carbon atoms. This has same number of hydrogen atoms. These are two isomers. Same formula, molecular formula. C5H12. There are 12. 6 plus 6, 12. This also have C5H12. When you have a structure, shape is the only difference. Same molecular formula in these two isomers. This is a unbranched. This is linear. This is called branch hydrocarbon. They branch off here. 3-methyl, 4-methyl group. This have less surface area. This has more surface area. Therefore, pentane has higher boiling point than 2,2-dimethyl propane, which is isomer has the same molecular formula. Both have same molecular weight. Dimethyl propane, 2,2-dimethyl propane, is roughly spherical, while pentane is linear. Linear molecule has more surface area. Pentane has linear molecule because it has large surface area and stronger dispersion forces between its molecules. Now we're going to talk about rest of the chapter in next class period. I'm going to stop the class for today. You guys there?
Yes.
I will see you on Thursday.